As I noted, this section consists of two different subjects, clearly distinguished subjects. The first part, here we talk about what's happening in the pressurized vessels. We discussed how to investigate stress state using the Mohs circle, and then depending on the position of structure, so we have different distribution of principal stresses, and then we have different magnitude of shear stress. And then we'd like to apply that concept to real structures. Here we're going to talk about what I mean in the second part. And here we're going to talk about what's happening, the stress state in girder problem, the beam problem, what I mean. And then in the third part, we want to talk about the stress trajectory, which means the change of the principal directions depending on the loading conditions. And then we'd like to revisit the concept of principle superposition, the 중첩의 원리. And then we'd like to generalize the concept to multi degrees of freedom to apply the principle of superposition to much more complicated problems. And then fifth topic is combination of different laws. And then in practical analysis procedure, we actually, combination of different load cases is very common. So we consider the various load with simple loading conditions, and then we sum up the results from the individual load cases to obtain the behavior of our structure for the real problem. Okay, now let's talk about the second part. The first part is stress trajectory. Before we talk about the stress trajectory, I'd like to revisit the concept of normal stress and shear stress found in beam problems. Here, to calculate normal stress in beam problems, we need the bending moment. Obviously, the bending moment depends on the position, isn't it? Depends on the position. Okay, depends on the position. So for example, let's consider my beam problem like this. So if you imagine the beam is loaded by the distributed load, and also we can consider the bending moment, no, not bending moment, concentrated moment, or the concentrated load. Then before our analysis, as I emphasize always, so we need to prescribe the coordinate system, the x direction, and then usually we denote this transverse direction by y coordinate, isn't it? So the bending moment depends on the position. The bending moment at point A must be different from the bending moment measured at point B. And the shear force too. The shear here the bending moment, and the shear force depends on the position, isn't it? And then the second term here, okay, look, this is y coordinate. So if you want to measure the stress at certain point, we'd like to measure distance up to this point. So y coordinate, isn't it, right? So that depends on the y coordinate. And the second moment of inertia, this is also depends on x coordinate, because, for example, so up to this distance, up to this distance, let's say we want to use a bigger cross section, and then let's say for the remaining part we want to use thinner cross section. In that case, our second moment of inertia must depend on the position of my structure. And then here, for the calculation of the shear stress, actually this is also depends on the position of x coordinate and at the same time y coordinate, because we have to calculate the first moment for the part where we want to consider the shear stress value. Okay, so basically the normal stress and shear stress depends on the position. Okay, so now let's consider simply supported beam here. So if you consider simply supported beam, and then the shear force diagram should look like this because of this concentrated load condition in the middle. This is shear force diagram is anti-symmetric. This is positive and minus. And the bending moment diagram is triangular because the derivative of bending moment diagram is equal to the shear force diagram. That's why here the shear force diagram is constant. That's why our bending moment diagram should be straight line to the loading point, and then the slope changes to the negative value because the shear force is negative. Okay, so now we want to check the stress at A, B, C, D, E positions. So for example, somewhere like here, okay? Then we can determine the shear force and bending moment. Then my shear force, the normal stress is given by the moment and the y coordinate and second moment of inertia. So because we already fixed the position where we want to calculate the bending moment and the shear force, that's why these two quantities, these are fixed. Okay, these are fixed. Only difference, only variable is the y coordinate, and then the shear stress is equal to VQ and IB here. And also, I'd like to say that the shear force and then the second moment of inertia, these two are fixed because we already determined the place where we're going to calculate the bending moment and shear force. And then the first moment Q, and then the width and the y coordinate depends on the material point in the cross section. So because the normal stress and shear stress changes, it is pretty natural to imagine that the stress condition is not the same. It's not the same. For example, if you look at at point A we must have the minimum normal stress, and then please note distribution of shear stress for the rectangular section that we discussed last time. This is the parabolic like this. So on the top and bottom surface it is equal to 0, and the shear stress is the maximum in the middle, isn't it? So at point A we have maximum normal stress. At point E, and then the situation is opposite. The normal stress is maximum here. And then at point C is near the neutral axis. At neutral axis, normal stress is proportional to y coordinate. That's why near the neutral axis, y coordinate is almost equal to 0. That's why there is no normal stress at point C. So we only have the pure shear stress condition at point C. And then here, point B and point D are kind of mixed condition. So in the case of point A and point E, its direction of the normal stress is coinciding with the principal stress direction because there is no shear stress. Okay, so exactly same, the principal conditions. Okay, and now how about point C? We have pure shear stress condition. So last time we already discussed this situation that if you calculate normal principal stresses, its direction look like this, isn't it? We can obtain that situation using the principle of superposition, or we can solve the eigenvalue problem. So please take a look at your 공업수학 textbook, engineering mathematics textbook. Then you can find how to determine the eigenvalues and also eigenvector. So just in case if you are not familiar with the eigen vector calculation, if I'd like to give you some more information for you guys. Actually, you have to do it by yourself, okay? This is just a service. Let's say you have sigma xx and then tau xy, and then tau, actually it's symmetry, the xy, and sigma yy, and this is stress state. And then if you consider dot product into certain direction ny, and then we can get traction. Tx and ty. But if we are, our direction is the principal stress direction, then the direction of traction is same as direction of the observation direction. This is a lambda times the nx and ny. Okay. So if you move this value into left hand side, then what's gonna happen is sigma xx minus lambda tau xy sigma yy minus lambda, and then here nx and y is equal to 0. Now how do you satisfy this identity condition? The first choice is nx vector is equal to 0. Actually, in this case, it's really trivial, isn't it? And also nx and y cannot be equal to 0 because this vector indicates a certain direction, so it cannot be equal to 0. That's why only condition is the determinant of this matrix should be equal to 0. Then how can we make the determinant is equal to 0? So sigma xx minus lambda, this is a quadratic equation, sigma yy minus lambda, and then minus tau xy square should be equal to 0. If you expand this quadratic equation, minus sigma xx plus sigma yy lambda, and then plus sigma xx sigma yy minus tau xy square is equal to 0. Then you solve for this, the quadratic equation. Then you can calculate lambda. So once you obtain lambda, then you plug in lambda here, okay? Plug in lambda here. Then you can make a relation between nx and ny, okay? Then you can determine the principal directions, okay? Okay, so once you determine the principal stresses and the directions, then we can easily find its direction here. For example, at point E, the direction of principal stress is in this direction. At the point B, and then is this direction, and the maximum direction is changing. So if you connect all, the principal stresses together, then we can obtain so-called stress trajectory. Here the solid curves are representing the directions connecting maximum positive principal stresses, and then the dashed curve are representing direction of minimum principal stresses. Let's imagine that say we are using concrete here. If you use concrete, then what happens? The stress-strain relation of concrete look like this. For tension, it is weak, and compression, it is much stronger than tension. Then it is very natural, in this case, the stress condition is symmetric. So we have compressive stress and tensile stress, and the magnitude should be the same. And then if any crack develop, let's say we are using concrete for the material of this structure, then where we have crack first? Then probably because this part is subjected to tensile stress, and then here it is subject to compressive stress. That's why the crack would initiate first, in the tensile part, isn't it, right? And also here, okay, and also here like this, okay, we're gonna have crack. That's why if you want to put any reinforcement, where we have to put the reinforcement, for this loading condition, if there is no, the loading condition is fixed and the stress condition is fixed as is, then maybe the optimum, mathematically optimal arrangement of reinforcement steel, 보강제 reinforcement steel, must be following the trajectory of maximum principal stresses. So maybe we have to put the reinforcement like this to reduce the tensile cracking, isn't it, right? But practically speaking, actually this curvy shape of reinforcement arrangement is almost impossible practically. We cannot do that, yeah? So instead, what we do in practice, we just put reinforcement in a straight line in the bottom where we have the maximum principal stress. And then look at this here. And the direction is going up. That's why here we anchor the tensile reinforcement here, so that we can resist the crack near the bottom. And then another layout that we can consider in practice is what? So we put the reinforcement, and then we'd like to kink the arrangement of reinforcement like this, typically following 45 degrees, okay? And then that is following the development of the stress trajectory near the support. And then the crack near the support around like 45 degrees, and we call it inclined shear crack. In 우리말 it is called 사인장 균열. Because of the name of inclined shear crack, people would think that crack is developed, because of shear force, but no, it is not. This is combination of shear force and the normal stress. That's why we have this kind of inclined shear crack. Okay, here we have an exam problem. In this exam problem, so we have to investigate the stress state in this cross section. Then to do so, first we have to determine the shear force diagram. So we have the reaction, and then if you determine the shear force diagram, first we have 3600, and then we have constant shear force up to the point of the concentrated load, and then we have the jump of the shear force diagram. The magnitude of jump is 10 and 800 pounds, and then we have another horizontal line until we meet point B. This is shear force diagram, and then the bending moment diagram can be calculated like this. So the maximum value here is integration of this cross section. What I mean, 36 pounds times, so 4 feet times 12, then that is the maximum bending moment at this point. And then using the proportional relation, because this is triangular shape, and then let's use the proportional relation. And then we can determine the bending moment at 0.9 inches from point B. So once we have bending moment, then we can determine the stress state at different position in the cross section. Alright, so next subject is principle of superposition.